This video will be a quick continuation of the previous, in which we used stoichiometry to set up our adiabatic flame simulation. In this video, we're going to be focusing on how we can use the conservation of energy to determine at what temperature the final flame will sit. Now again, to redraw the model of what's happening, we have here our Bunsen burner, which takes in natural gas, which I'll just say CxH2x, because again, we discussed in our example there will be three of them. It will be 95% methane, I'm just going to write meth for short, 4% ethane, and 1% propane. I don't know if I discussed the actual delineation of our natural gas, but that is the percentages we're going to go with for our composition. And also we have going in is our air, which is 21 to 79 oxygen to nitrogen. And also for the initial conditions as well, all of this is coming in at room temperature 298 Kelvin. Obviously in here, it reacts, emits energy. We're assuming none of it is lost to the outside air. We're assuming it's adiabatic. So again, the overall heat lost to the metal and to surroundings will be zero. All of the heat will be contained in the final flame. It's a really bad flame, but it is what it is, which is going to be at some temperature T, and obviously is going to contain all of the excess flow through of carbon dioxide, H2O, and any excess air that we're pumping in, which is 20%. Now, for our energy calculation, it's actually fairly simple because we're going to assume quite a few things. We're going to assume that the velocity of what's going in and what's going out are the same, so there's no velocity calculations. Since it's a gas, we're not going to worry about gravity or any like vertical energy. So, and also because it's adiabatic, we know that the energy change, because again, energy balance is energy change is equal to E in minus E out plus E generated minus E consumed. But because all of the energy that is generated during our reaction actually comes from the molecules themselves, because we're not accounting for flow rates or anything like that, because we're assuming the flow is the same, we can actually say that because it's adiabatic and no heat is lost, the energy change is actually equal to zero. It becomes a steady state system where things flow in, fire comes out, and the heat lost as the energy comes in from the ingredients for combustion, and the energy that comes out after heating them in this flame after the reaction takes place, there is no loss in energy. The amount of energy coming in the molecular bonds and the amount of energy leaving in molecular bonds and extra heat energy are going to be equal. So because of that, we can say zero is equal to the energy in minus energy out. Again, we said we're only focusing on internal energy, so that's going to be the internal energy H in times the mass flow in minus the internal energy out times the mass flow out, right there. But again, we said we're going to assume the flow in and out are equal, so these are both going to be the same, so they can just be factored out, divided, and then 0 divided by any number is still 0. So we have 0 is equal to the internal energy. However, because we're talking about molecular bonds for the energy, because the only thing coming in is obviously the heat contained in the temperature and the molecular bonds, we can actually describe enthalpy in such a way. We can say it's the heat capacity of every single one of these substances, because this is done for every substance. The heat capacity at room temperature, 298, multiplied by or not multiplied by per se, but in addition to, because this is all heat, so this is all being included. This is internal energy, plus the energy of the bonds of formation of all of these things, plus we're going to call it HF of the I don't know, out of H fuel. There we go. This is enthalpy. So the enthalpy of the fuel minus the heat capacity, the amount of heat each of these substances are storing at our final temperature T, because again, we're heating it up and that's where our energy is lost. I'll put that in parentheses as well. Plus, well, all the energy that was transferred from the original bonds in H fuel is now contained in all of the output So again, our H2O, our water, and our CO2, and also any excess air that came in that would be counted in H fuel and counted out in H fuel. So we'll just call that H EMM for emissions. So we know that the heat contained by our substances and the energy that it took to form them from their natural states, when subtracting from the heat taken away, the energy taken away in the form of heat contained by each emission, and the energy that it takes to form the bonds, have to be equal. So we can solve this for T by basically moving this over here and saying that the heat capacity Cp at the temperature T must be equal to the heat capacity of the inflowing substances at the temperature of 298 Kelvin, or room temperature, plus the enthalpy of the fuel minus the enthalpy of the emissions. So this right here takes care of the energy stored as we change molecular forms, and this right here covers the difference in heat between what's coming in at room temperature and what's going out. And what's important is that we actually know how to calculate the heat capacity of something at a certain temperature. That's covered, it's called equation 107, I'll draw an arrow. EQS 107. That's actually covered in Python. There's an equation specifically that allows you to calculate the heat capacity of a substance, the amount of energy that substance holds at a certain temperature. And so we'll use that in Python when we go through and simulate everything. So thank you, and have a good afternoon.